Thus far in Proton NMR, we've seen that the number of signals tells us about the number of proton environments. This is because each proton environment experiences a different external magnetic field, or a different effective magnetic field, and therefore requires a different radio frequency for the alpha to beta transformation. The NMR signal can also be correlated to the specific type of proton environment. This chart that we see here in teaching model number 4 gives you a sense of that. So for instance, if we have CH3 groups or CH2 groups as implied by this category right here, we're going to expect to have a shift around 1 to about 1.5. If the protons are adjacent to a pi bond, such as in this example right here, we would have a shift from 1.5 to 2.5. By the way, we refer to a proton that is on a carbon that's right next to a pi bond as an allelic proton, and we will come back to that later. If we have protons that are adjacent to a halogen or a nitrogen or an oxygen, because these groups are relatively electronegative, we're going to have substantial de-shielding, and therefore we would expect to have a signal somewhere between 2.5 and 4.5. If we have a proton directly on a carbon that's making a pi bond, and we refer to that proton as being vinylic, well then we'll expect a shift around 4.5 to 6.5. If we have a proton on a benzene ring, in other words, a proton that's involved in an aromatic system, 6.5 to 8. Finally, if we have protons on a carboxylic acid or an aldehyde, we would expect shifts around 9 to 12. Now those are the major categories. We can in part predict trends. So for instance, if we look at this first row here, starting from a CH3 group, a typical CH3 is going to have a chemical shift of around 1 part per million. If you add an iodine group, which of course is more electronegative than a hydrogen, then the remaining hydrogens experience de-shielding and therefore chemical shift at 2.2 parts per million. You change the iodine for a bromine, which is even more electronegative, there's more de-shielding and therefore chemical shift to 2.7. All the way to fluorine, which of course is the most electronegative, and even more de-shielding. So all of this is quite predictable, and we would say that there's an increase in de-shielding. If you consider having only one substituent, such as in this case right here, well then we'd expect the chemical shift to be around 3.1 parts per million. But if you add another of the same substituent, well the chemical shift is even greater. There's even more de-shielding. If we look at this example right here, you can see that having 3 chloro groups gives a chemical shift similar to an aromatic system. So be careful when you interpret signals. If you see a signal around 7.3, yes, initially you may think that it's aromatic, but it may not be. It may be the fact that there are a couple of de-shielding groups present. Also, the degree of de-shielding depends on how close to the electron withdrawing group. So in our last example in this chart here, you can see that the protons in this region are shifted quite substantially because they are right next to the chloro group. The protons in the CH2 group, found in this group here, are only modestly shifted, and that's because they're not quite as close as to the electron withdrawing group. And finally, the CH3 group that's right here, those protons essentially are not affected at all by the electron withdrawing group. So the proximity to the electron withdrawing group is important. You might be wondering why vinylic protons are shifted so much, or why aromatic protons are shifted so much. One way to have a chemical shift is because of de-shielding, and therefore the protons experience a greater effective magnetic field. But another way to experience a greater effective magnetic field is the result of an induced magnetic field. So the example here on the left is the example of the aromatic proton. The electrons that are in those aromatic rings, such as the benzene ring, are what we would say delocalized. The electrons are not localized with any one particular carbon. And while it's not a great analogy, we can kind of think of them as having motion throughout the ring. As a result, these electrons create an induced magnetic field. As it turns out, the induced magnetic field happens to actually be aligned with the applied magnetic field. And therefore, those protons, in a sense, experience a greater effective magnetic field. So this is not a deshielding effect, but an effect due to an induced magnetic field. The same sort of thing can happen from a carbon-carbon double bond, where you have a proton on that carbon-carbon double bond, so that's a vinylic proton. As it turns out, once again, the induced magnetic field, because of the pi system, happens to align with the applied magnetic field, and therefore a greater chemical shift. The same thing is true if you have a carbonyl group. So that's what's being represented here. A carbonyl group and a proton that's on that carbonyl group will experience a greater effective magnetic field because of the induced magnetic field. You, of course, will have this chart available to you when you're doing various exercises and the midterm and the final. Therefore, it's not necessary to memorize any of these numbers, but you should become quite familiar with this chart. Notice that we talked about the idea of saturated protons, so that would be in this region right here, all having a chemical shift near 1. But it does depend on whether or not it's a CH3, a CH2, and a CH. The more carbons that are attached to a carbon, and where the proton is, the more deshielding there is. Now, it's a modest effect, but it does make a difference if it's a CH2 or a CH. This chart doesn't show all possible examples. So for instance, right here we see a CH3 group next to a benzene ring. The chemical shift there is around 2.3. If you think about the situation, therefore, of having a benzene ring and a CH2 group, you would expect the chemical shift to be around 2.3, but then again, you know that CH2 groups are shifted a little bit more, so maybe the chemical shift would be around 2.5, 2.6. So this chart doesn't contain all possible combinations, but you can extrapolate in terms of what to expect. You may notice that some signals are indicated here as being variable. So often these signals are associated with protons that are on nitrogen and oxygen, and it's because these protons, comparatively speaking, are relatively acidic. So the protons exchange with the environment. Therefore, their signals are not as pinned down, if you will. There's another feature of those signals that we'll be talking about a little bit later on. To finish this little segment here of video, I'd like to look at this exercise and look at the examples in the first row. We will do the other examples in a synchronous class. So notice that each structure is labeled with 1 and 2. So these, of course, correspond to different proton environments. I'd like you to predict which environment you'd expect to have a greater chemical shift. So at this stage, you know that, of course, the proton in the aldehyde would have a greater chemical shift versus the proton that's part of a CH2 group. You might be wondering, however, why it is that this proton here has a greater chemical shift compared to the proton labeled number 2. Well, I'd like to remind you that the proton labeled number 2 is part of a CH3 group, whereas the proton labeled number 1 is part of a CH2 group. So although both of these have the same proximity to the electron withdrawing group of the chlorine, a CH2 group generally has a greater chemical shift than a CH3. In the last example, we once again have a proton on a CH3 group and a proton on a CH2 group. Both set of protons are near the electron withdrawing group of an oxygen. Again, however, because number 2 here is a proton that's part of a CH2 group, we'd expect a slightly greater chemical shift.